So I was like running out of time there. I don't exactly know where it broke, but I said that this is a prediction physics, mates. And the prediction is that since higher frequencies means higher energy, it means that when you go to higher frequencies, the output from the oven should go up like this. But when they did the actual experiment, the output of energy went like this. And this has to do with that light is quantized. And like I said, depending on the frequency, it determines the amount of energy. Higher frequencies, more energy, lower frequency, less energy. And a quanta is a minimum amount of energy you could send out, and that's determined by the frequency at minimum amount. So if you have a higher frequency, you have a higher amount of energy that is required to make that quanta, and you can't send out your energy or that light. You can't send out that light without meeting that minimum energy requirement. That means that. But did they realize the full impact of this? I'm not sure, but we do understand that today, and I want to exemplify this with the two slits experiments. So if we have light, which we think about as a wave, and if we send it out to the two slits experiment here, the wave will hit the two slits, and because it's a wave, it will create it will pass the slits and then spread out and hit the screen and then create the interference pattern. And I've talked about this in my previous video about observables and non-observables. The thing is here now, so if light is a wave, okay, then it means we should be able to detect that wave here, right? So we could set up detectors here. And what happens when we wait a second, roll back. Light is quantized, and if we want to watch those quantize, we could that light beam that goes out there, we can dim it and until it's so weak that we only get one quanta at a time, which is called photon. And it's possible to do this. You can send out one photon at a time. And the thing is here, you don't get this interference pattern, but when you send photons, you have to think of a photon is a particle. And why do we call a photon a particle? It's because in these two slits experiments, when we're using light and we're sending out photons, we get the same pattern as we get when we send a quantum particle through the slits. We get something. We get a position on the screen. We don't get this. We don't get these lines. When we dim down the light far enough, we get small spots like this on the screen. The reason we get lines when we're using light normally is that there is such an enormous amount of photons that goes out from light. So it looks like continuous stripes on the screen, but it isn't, because when you dim it down, the quantified natures of lights came, no pun intended, into light. So we may expect that if we put a detector here, maybe we get the same behavior as we do from a quantum particle. But remember, light is a wave, right? So that means that okay, so we can detect a photon here, but since it's the wave, it should also pass through here and still produce the interference pattern. So we can do that experiment by trying to detect the photon in the wave here. And when we do that, what we get is a pattern like this. And that pattern is a pattern of a particle. But you could say we already know it's a particle because it's been detected at a certain point here. So we know it's a particle. But the point is, the interference pattern goes away when we try to detect it. Exactly the same setup as we send a particle through it. The point I want to make here is, I have to check the time. The point I want to make here is, traditionally, we've been thinking about light after a long debate among naturalists as being a wave, because light has been behaving like a wave. Light. And traditionally, we've been thinking of quantum particle, actually an electron. So we've been thinking about electrons as particles. Electrons. We've been thinking about them as being particles. And the reason for them is because like electrons are few in numbers, they move very slow, and we usually see them as a point detections. Light is huge in numbers, they move very fast. It's very hard to determine a position from them because of that. You can't grab them in flight, as to say. Oh, well, actually, you can grab them in flight in a slits like this. But when you do, it turns out that they create a point thing here. So if we have, like what I talked about before, our experiment sets up where we have a source and a target. Then, with the electrons, we have an event here, and then we have a target where we register an event. And an event, as I said before, is a position. So you have one position here which that happens something, and then you have another position where there happens something. And if you send electrons through in this experiment, so we say this is A here and B here, A, B, A, B. These are these events, and at the target we get some kind of pattern. And if you have this setup here, that we make an observation here and an observation here, then we observe an event here and something emerging here, and then we see this pattern there with the electron. If we have light and do the same thing, we have an event here and an event here. That's what that experiment with the light shows. When we dim it down, it becomes exactly the same as with the electron. Then if we go in and try to detect which slits the electron passed, then we get this thing. That is to say, we create a new observation C here, and that's the slide here. That's the C. So you have those observations A, B, and C. A, B, and C. Yeah? If you only do A, B observation, you get an interference pattern. If you add the C observation here, you get the particle pattern. And it doesn't matter if you send an electron or light through there. So now the question is so do you think that light is a wave? That's kind of like how I think about it. I'm not saying that what I'm thinking is the truth, but I'm saying like my when I'm looking at things around me in the world, like, yeah, light is a wave, electrons are particles. And the reason I would say we think light is a wave is because it behaves like a wave. And the reason we think electrons or other stuff with that thing is particles is because, like, in our everyday life with particles, we do this the assumption of persistent existence. When we send an electron here, we assume the electron exists here, and it exists there, and that's the same electron which we sent over from here. That's an assumption we do. And then, like I've talked about that box experiment, where we have a ball here and ball here, and we go here at 12 o'clock and 12:01. At 12 o'clock we observe it here, at 12:01 we observe it here, and then we ask ourselves, how did it get there? And that's an assumption of persistent existence that makes us, if we observe the moving a little bit here, that it's been moving in a trajectory, and that this is the same object as this thing here, but it's just been moving, it's displacing itself in space from here to here. That's the assumption we make.